All right, we're going to keep going with the April 29 to May 3rd SI sheet with problem number 4. It says draw the ring tautomer of the following molecule. Similar to a keto-enol tautomerization where a molecule can kind of exist in two states, we're doing a ring tautomer. So we are presuming that this molecule right here can also exist as a ring, and we'll show how that happens. So the H plus here right now that it's talking about, a mild acid, is going to protonate the oxygen in the aldehyde group, and so it forms a, as the oxygen abstracts that hydrogen, it forms a positive charge on the oxygen, which kind of gets translated throughout this aldehyde group right here through resonance, and you form a more favorably, it makes that positive charge on the carbonyl compound even more pronounced, to the point that the lone pairs on the alcohol will actually come in and nucleophilically, these electrons will nucleophilically attack that carbonyl compound, or carbonyl carbon now. And so that's what you're seeing there. And then so it allows these electrons from the carbon oxygen double bond to move to the oxygen to eliminate that positive charge that was on the oxygen. But the oxygen from the alcohol now has a positive charge, as it gave some of its electrons to the carbonyl carbon. And so what you'll see is that whatever conjugate base there was to this acid will come and abstract the proton from the oxygen from the hydroxyl group that attacked the carbonyl compound, the hydrogen that's on this green oxygen. The conjugate base will come and abstract that hydrogen, allowing the electrons from that oxygen-hydrogen bond to come and eliminate the positive charge that's on the oxygen, and you'll be left with this product right here. And so that's the ring tautomer that can be formed from this aldehyde alcohol, from this starting reagent. And it's a hemiacetal, which is a little more stable than a compound that has a aldehyde and an alcohol in it. So moving down to number 5, it says give the final product of the following reaction. And this is a really similar reaction where sulfur is a group 6 element, and so it's going to act just like oxygen. It has those lone pairs of electrons just like oxygen. So in this example, you can think of the sulfur acting just like the oxygen. So in the first step, the hydrogen the proton is going to protonate this oxygen, giving the carbonyl compound, or carbonyl carbon, even a more pronounced partial positive charge, and the electrons from the sulfur are going to come in and attack that. And so you'll form that a similar ring to the example above, and in this instance, the proton can further protonate the OH group that's on that, or that's going to be formed there, and that group can leave as water, leaving a positive charge on that same carbon, and then the electrons from this sulfur can come in and attack, forming 2 closed rings. And so that is answer choice D. And the mechanism, I didn't go into as much depth on that mechanism, but it's really just electron pushing, and you do it the same way that you do example number 4. You just kind of do it 2 times. And so moving down to problem number 6, it says which of the following can form the cyclic hemiacetal in the presence of acid. So I want to take a second to clear up some vocabulary, because it was a little confusing to me. And so an ether is an oxygen with two R groups attached to it, so two carbon groups attached to an oxygen. An acetyl group is different than an ether. Acetyl and ether are not the same. And so an acetyl is an R group that has two OR groups attached to it. So, I mean, that's what an acetyl, and they react and act and just live differently than ethers. And so a hemiacetal is where you have an R group that is bound to an OR group and also a OH group. And so this is a hemiacetal right here. This is the carbon that we're talking about. It's bound to an OR group and it's also bound to an OH group. And so if you remember, I'm going to scroll back up to example number 4 here. The product that we formed involved, this carbon is the same carbon that we'd be talking about, where it's bound to an OR group and also an OH group. So this is a hemiacetal, and the bond that formed, if you paid attention, was this oxygen carbon bond right here that's in the ring. And so if we come down, the way I approached this question is I said, okay, well, this is the bond that's probably forming. So if I open up that ring structure, then I've got something that looks like this. And I know that this oxygen was, in example number 4, was the alcohol group, and then this alcohol group right up here, that started off as the ketone group. I'm going to scroll up one more time to example number 4. You see this aldehyde group, sorry, I think I said ketone before, but this aldehyde group right here ended up forming this alcohol group, this hydroxy group, OH group. And so that's kind of how I approached it. I did the same thing in reverse. And so I looked at my answer choices, and it turns out that this product right here is the same as D. It is drawn a little bit differently, but if you can kind of rearrange it in your head, and you can even count the carbons, whatever, 1, 2, 3, 4, 5, 6, where this is 1, 2, 3, 4. Oh, 1, 2. Did I? Oh, sorry. I miscounted up top here. My bad. I was wondering what happened there. So 1, 2, 3, 4, 5, and then that oxygen is number 6. And if you look there, it all lines up right. So the answer is D.